Hi everyone, I'm Agrim and today I will be presenting WiForce, a new wireless sensing modality capable of sensing and localizing contact forces. While interacting with objects and people around us, we humans are accustomed to obtaining a rich force sensing profile via our skin. In other words, we get a feel of where and with how much force is any interaction occurring with. However, robots do not have this comfort yet, and at best, robots can sense some discrete forces. Without an accurate sense of force profile, it is difficult for robots, say for an example, to ascertain if they are grasping an object firmly or softly. Thus, we need to have a skin-like layer for robots, which allows the robots to feel the same sensing richness we as humans are accustomed to. Another important application is for in-body surgical robots. These soft, flexible robots need to traverse through tight spaces to operate on organs. And here, we are interested in obtaining force profile as a surgical robot interacts with the organ, which allows for easier and safer surgeries. Now, let me show you how these sensor skins are designed currently. To sense force along the length, these skins are populated with multiple discrete force sensors, which show voltage variations as forces are applied onto them. And these voltage variations are then sensed via an extensive network of wires. And this forms a big limitation with this and hinder a lot of use cases. For example, let's revisit the surgical robot use case. We covered the sensor skin with these discrete force sensors. And now, to sense the force profile, we need to run wires till each sensor. Imagine putting all these wires on these small centimeter scale robots where space is at a premium, and this solution will never scale. A possible way around this is to wirelessly communicate the force profile, completely bypassing the wiring problem. Thus, we present WiForce, which makes a headway in this direction and creates a wireless sensor capable of force sensing with sub-Newton accuracy as well as millimeter level localization. Before taking a deep dive into WiForce, let's take a look at a possible wireless extension to the wired sensing password. Today's force sensors give voltages as outputs, which can then be digitized and sent over wireless communication modules. However, first, this typically requires power-hungry electronics, which might also require a battery or an energy harvester. Second, the multiple data streams emerging from these sensing points further exacerbate the power requirement. Typically, research into this direction goes in either making communication lower powered, which still requires additional electronics, or reducing the number of sensing points by improved interpolation across sensors, which sacrifices accuracy. So, can we make a jump to a new class of sensor design which avoids power-hungry electronics and achieves accuracy? To design such sensors with no power-hungry electronics, our key insight is to eliminate the inefficiencies due to separate sensing and communication blocks by combining them to a mechanism which can sense and communicate at the same time. Let me show you how to do it, and we start with the flexible skin-like layer, which starts to bend and deform as a function of exerted force. To sense and wirelessly communicate this force, what if we could attach an antenna such that a deformation caused by this force gets encoded onto the reflections of the incoming wireless signals? Hence, with this approach of encoding force onto the reflected signals, we can eliminate the need for power-hungry electronics and achieve a unified sensing and communication mechanism. And this forms a driving design principle behind WiForce. So, how does WiForce encode forces onto the reflected signals? Let's model the flexible layers as parallel beams. And when a force of Fc starts acting at location LC, the top beam bends and comes into contact with lengths L1 and L2 from the ends of the bottom beam. Both force and its location can be described as function of these two lengths. As force on the top beam increases, it bends more and L1 and L2 decrease, and this beam bending effect forms the basis behind these two functions. Thus, if we can communicate these analog quantities L1 and L2 wirelessly, it will allow us to sense as well as localize the forces. To achieve this communication, WiForce connects antennas to the top beam and with the bottom beam acting as ground, and this structure now starts receiving the green wireless signals. Let's imagine the same force which I showed on the left is now applied. When you apply this force, really what happens is that at these contact points, electrical shorts are created and the signal gets reflected around these shorts, shown in orange and pink here. The length L1's information therefore is encoded in the orange reflection going back, and similarly for L2 with the pink reflection. Therefore, in summary, we have shown a mechanism which encodes the contact lengths onto the reflected signals. Let's now understand how exactly WiForce measures these contact lengths L1 and L2 wirelessly. For now, let's focus on one side of the sensor with no force acting on it. And here, the signals will travel the total length of the sensor and accumulate a constant phase over time, which will be proportional to the total travel distance L. Next, when we apply a force, the top beam will bend and create a short, which leads to signal traveling lesser distances, L1, and this shows up as a phase jump over time. And it is precisely this phase jump which WiForce measures to estimate L1. However, can the same thing be done from the other side of the sensor as well to measure L2? To estimate L1 and L2, we now need to consider both ends of the sensor. Therefore, the wireless reader needs to read these phase changes at both the orange and pink signals to infer the force and its location. However, the orange and pink signals interfere with each other, and thus the reader cannot estimate the phase changes on these signals individually. To solve this problem, WiForce augments the sensor design with RF switches at both ends of the sensor. Let's consider the orange switch for now. Toggling the switch on and off will basically connect and disconnect the antenna to the sensor. And this on-off toggling creates frequency shifts in the reflected orange signal, and the created shift corresponds to the toggling frequency F1. Similarly, the pink switch can toggle at a different frequency F2, and this would prevent interference at the reader. Does this solve the problem? Turns out no. Recall that to measure lengths, we measure phase changes from when the sensor is pressed to when the sensor is not pressed, and in the unpressed configuration, the two ends have a wide open passage between them. Here, the signals will travel the entire length before reflecting off the other hand. And this happens when one switch is on and the other is off, such that a sensor is connected only to one antenna at a time. This is a desirable situation. However, when both the switches are on, sensor is connected to both the antennas, and the signals from one end get transmitted through via the other end, which does not allow for isolation of these orange and pink signals, since now they will superimpose. And this is similar to the proverbial saying that one sheath can't hold two sharp swords, as both of them will wear each other out. Thus, the challenge here is to give two frequency shifts without the switches being on at the same time. WiForce comes up with two solutions here, and the first solution is to toggle switches one at a time. However, this will fail to capture both L1 and L2 at the same time, leading to higher latency and other system level issues. The insight we have here is that why not redistribute the off time to make this modulation continuous? And this redistribution actually takes the form of duty cycling and gives continuous modulation at two different frequencies having 25% duty cycle, which allows us to measure the two lengths simultaneously, thus incredibly improving the system design. Since we have modulations at two unique frequencies now, which will not interfere, we can just use a single antenna to sense phase changes from both the ends. And in this way, communicating two-side phases using just one antenna allows us to reduce the form factor. So far, I have covered the design aspects of the sensor, and now due to the short duration of the talk, I will go over on a high level how WiForce's novel reader estimates these forces. The reader consists of two antennas, one to transmit the green wireless signal that the sensor reflects, and these sensor reflections are then received by the receive antenna. A main challenge with the reader is to isolate these sensor reflections from the other reflections bouncing off due to multipath. To address multipath separation, as well as make our sensing compatible with commercial equipment like Wi-Fi routers, we built our reader to work with Wi-Fi-like OFDM signals instead of narrowband tones. This allows us to utilize the wideband nature of the OFDM channel estimates and use a Doppler transform to isolate the sensor reflections from both the ends, which show up as artificial Doppler frequencies. And these artificial Doppler frequencies have equivalent physical speeds which exceed 70 miles per hour. And this much high speed cannot be generated due to common sources of multipath like furniture and walking people. Finally, we also extend this algorithm to sense phase changes at these two artificial Doppler frequencies with about a degree's accuracy, which enables sub-Newton force sensing in millimeter level localization. More details on this algorithm can be found in our paper. To implement the sensor, we augment a simple microstrip line with a soft polymer beam on the top to efficiently utilize the mechanical beam bending. First and foremost, to benchmark our sensor, we apply forces using an actuator and get the ground truth force from a standard force sensor, and we measure the phase of the sensor reflection via a wired setup. As we increase the force, the beam bends more, and thus the phase accumulated increases further, giving about 25-degree phase changes, which allows us to sense multiple force levels using reflections. For this result, we replaced the wired phase measurement setup with measurement using wireless reader implemented on a USRP. Due to effectiveness of the reader algorithm, we get almost as good performance as compared to wired benchmarks. We profile this wireless performance with CDF plots and obtain sub-Newton accuracy, And similarly for force location, we get millimeter level accuracies. Our sensor is designed to work across the entire 0 to 3 GHz bandwidth, and we show results in the two most popular bands here, 900 MHz and 2.4 GHz. 2.4 GHz is supported by Wi-Fi and Bluetooth and allows for reading with such technologies, whereas 900 MHz is a suitable frequency for in-body propagation. Which leads us to our next test setup, where we replace air as the propagation medium with layered tissue phantoms, fabricated to mimic the human body composition. And we observe that this change of propagation medium does not affect our performance by much, since we get almost the same median error as compared to over-the-air testing. And many more results like testing with multiple sensors, as well as detecting and localizing fingertip forces are there in our paper. To conclude, I would like to provide a larger context of force sensor research. A 2009 research work on MOSFET sensed force profiles by having force sensitive resistors crisscrossing the surface. Over the next years, people realized that it is infeasible to have this much wires and have tried to replace them with discrete electrodes, which reduce the wiring requirements along the surface. However, they are still bedeviled with the sensing wires. And in this context, WiForce eliminates the sensing wires altogether by sensing phases instead of voltages, which can be interrogated more simply by just shining RF radiation on the sensor, unifying sensing and communication. Being totally wireless and significantly low powered, WiForce still achieves some Newton millimeter level sensing accuracy, and there are some interesting directions which can be enabled in future by our work, right? Can we extend WiForce to other related quantities to force, like let's say blood pressure? Can we enable newer use cases in the direction of VR and AR, which might also benefit from WiForce's low-powered force sensing modality? And finally, can we enable a new wireless sensor suite for robots by combining WiForce with previous works on wireless tracking and localization? Feel free to contact me at my email address for more information about our research. You can also follow updates on our research on our project webpage. Thank you.